Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another continuation of an introduction to trigonometry, specifically angles. We're in the midst of learning angles or relearning angles and learning about a new angular measure here. This video is dedicated specifically to radians. This is the heartbeat of trigonometry as far as measurement goes. So what is a radian? A radian is actually, so before I even begin to define it, a radian is what any other species with intelligence would be able to understand. If you were to state, this is how we measure angles, they would say yes. But if you said, oh, we just split a circle into 360 degrees, they'd probably say, why would you do that? That's a dumb idea. So a radian is universal, whereas a degree is really just a man-made construct or a human-made construct. It doesn't really make sense to any other culture, but a radian makes sense to everybody. Well, everybody who understands it, that is. So 1 radian is the measure of a central angle of a circle that intercepts an arc equal in length to that circle's radius. Now that is a beastly definition. It sounds terrible, and I'm sure I could have written it better, but I actually did not write that. I kind of copied that, but there is a much better way of saying it. 1 radian is the angle necessary to cut out an arc of length r along a circle of radius r. Imagine a pizza or something like that. So let's go ahead and just create one. And this pizza here has an edge to it. It also has a radius, by the way. I'm not going to tell you the radius on this one just because I don't know what it is. But I've just placed a dot on the center. So if the screen wiggled a little bit, that's what I did. And what we're going to do is we're going to cut out an arc that looks to be about the length of that red radius line. So it's hard to tell with an arc, right? You might say maybe right around, maybe around here or so, something like that. That looks to be an arc that's of the same length as that red radius line. So let me move this box out of the way, or this protractor out of the way. I'm going to connect up, and I'll actually use red to connect these up. So the claim is whatever that radius was, it's radius r, right? We're claiming that that length, that arc is of length r. If that's the case, if all those match up, then we're defining that very special angle, this guy right here, we're going to define to be 1 radian. And that universally makes sense because now, okay, imagine that's 1 radian. Okay, I'm going to go ahead and zoom out a little bit. I'm going to make this circle much larger. I'm going to put a pin right there. I'm going to go ahead and drag this on top of that pin if I can. Okay, and I'm going to do the same thing. I'm going to start cutting out an arc, and I'm hopefully going to get an arc that's about the same length as those red lines. That's roughly, wouldn't you say that's about it right there, maybe? Something like that. Any larger and it would probably be too large. I'm also cheating because I kind of know the value of a radian, but you would hopefully agree that those red lines are roughly the same length as a black line. And so let me move this off here and let me connect those two up. Now this is not the same radius as in that first picture, is it? It's much larger. So maybe I'll call this S. So that's S, it's a radius S. Well, then this arc length is S. But the reality is, if the arc length matches the radius, that is 1 radian. It's still 1 radian. It's independent of the size of the circle. It will always cut out the same size for 1 radian. If I make my circle this large, let me put a pin in the center. Drag that back over. If I make my circle that large and I go ahead and just do this. Oh, I drew too far. Hold on a second. Let me move this out of the way and park this back on there and actually get the right pen. Okay, perfect. And we'll try it again. Again, I'm trying to get this arc length to match. Notice I keep stopping. That was an accident. I don't need to stop at 60. 60 degrees is not 1 radian. But it's roughly, I mean, if I continued forward, let's say I just continued forward, you'd have to agree that that length right there is much larger than the 1 radian. So I'm saying that probably that length right there is the right length. And we're going to connect those up again. So there's just some new radius here. It's much larger. I'll call this T. This T. Well, if the arc length matches the radius, in other words, T is the arc length, if T is the radius, then, again, by definition, this is 1 radian. Very beautiful theory here. So this begs the question, well, how do you get to 2 radians? Well, that's actually pretty easy, and it's not the purview of this section, but to get to 2 radians, I'll just double up the length right here and I will have 2 radians. In fact, let me go ahead and erase one of these and let me zoom in too. Okay. So I threw down, not so appropriately, but good enough. And let's suppose that you want to increase this from that length to maybe twice its length, right? So if I go to twice its length, maybe right around here, maybe a little bit more, who knows? Somewhere right around there. That looks like 2 of those R's. Let me move this out of the way. That looks like 2 of those R's. So the arc length is 2 of those R's, or 2 radians now. So let me draw that in there. And in fact, what I'll do is I'll erase this piece right here, and I'll erase that number 1, because now we've opened twice as wide. This is now 2 sets of radians, because this full arc length right here, which I didn't mean to draw right there. So let me hit undo and let me turn off my protractor because that's annoying. But that arc length is now twice R. So you should start to see a relationship between the arc length and the radius. If I wanted to go to 3 radians, I would go ahead and again start at the edge there and just rotate over. And I would go to, let's see, I have to do the math in my head, I apologize. Right about to maybe here. Somewhere right around there. Maybe even a little bit further, actually, to be honest with you. So I'll just put a little bit of extra oomph on that. And now let me get this guy out of the way because it caused me an issue last time being in my way. So that would be 3 of those arc lengths R. So there'll be 3 of them. And that means that we have rotated all the way over to 3 radians. Notice it wasn't 180 degrees. So it's not exactly flatlining here. This is the horizontal axis. We haven't gotten all the way to the horizontal axis, but notice the relationship between this arc length, which I'll just call this arc length S for right now. So arc length, actually, maybe I shouldn't. That might confuse people. If you look at the arc length, and if you divide that by the radius, it should equal the number of radians. And this is a very famous formula right here. And we'll actually come back to that. But I just want to introduce that right now. If you take the arc length and divide it by the radius of the circle, arc length of what you cut out for the angle, divided by the radius of the circle, it will equal the number of radians you have cut out. And we let S equal arc length, because that's a traditional letter that we use for that. And we get the following. S over R is equal to theta, where theta must be in radians. It's not in degrees, it's in radians. So anyhow, that's not the purview of this lecture, but I just wanted to start kind of getting that into your brain. Now, it is critical to note that radian measure is unitless. That is, an angle of 3 degrees is definitely an angle in degrees because it has a degree sign. But 3, if it doesn't have a degree sign, is an angle in radians. So when you see, and you're talking about angles, if you see a number without units, or if I do, I immediately know that student or that person is talking about radians. This fact will be highlighted later, but it is incredibly important. And then this theorem, such a beautiful theorem. A full circular rotation is 2 pi radians. That is like the birthplace. Here we go. Trig. Full circular rotation is 2 pi radians. So let's do the proof. And the proof is kind of nice. So let's suppose that we start with a circle of radius 1. There we go. Just rotate it around by a full 360 degrees. And we have the circle, and I'm going to plot here, hopefully in the center. I didn't mark it out earlier, but we're going to plot out a radius of 1. That's our radius. And we know that 1 radian is the angle needed to cut out an arc along the edge of length 1. So I'm going to say that's roughly 1 radian right there. Okay. I'm not saying it is exactly 1 radian, but I'm going to say it's 1 radian roughly. And that's mainly because, again, this arc length is 1. Okay. So how many more do I need to cover the whole circle? Well, it's a unit circle. So the question is, what is the circumference of a unit circle? Remember the famous circumference formula. Circumference of any circle is 2 pi r. But in a unit circle, the radius is 1, which will imply the circumference is 2 pi. So to extend that red highlighted region here to go all the way around, I just need to multiply it by 2 pi. I need 2 pi times that to get all the way around, which means I need 2 pi times this to go all the way around. So 2 pi times the outer edge will get me all the way around. 2 pi times that angle will get me all the way around, implies there are 2 pi radians in a full circle. Now, if you don't like that version of the proof, there's actually a better version, which uses the formula we just mentioned a moment ago. I wrote this down on a previous page. It was that the arc length divided by the radius is always equal to the angle. Again, that angle must not be in degrees. It must be in radians, right? And so if I say we're on a unit circle, that would imply the arc length is always equal to, because you're dividing by 1, it's always equal to theta, again, on the unit circle. But we've just stated the arc length for a full rotation on a unit circle is 2 pi. Thus, the circumference being 2 pi for a full unit circle means that the angle for a full unit circle, or for a full circle in general, is 2 pi. Such a beautiful idea. So there are 2 pi radians in a full rotation. Very important. So let's sketch some radian angles. And these will all be sketched in standard position. Again, where the initial side points towards the positive x-axis. So alpha is 2 pi radians. Notice none of these, except for the last one, has a degree sign. So all of these, except for the last one, all these are in radians. So 2 pi, I'm going to, again, positive angles open counterclockwise. I'm going to rotate a full circle. This angle is 2 pi. Some people will ask, do I need to write the word radians? The answer is no. If you don't write anything after that, I know it's radians, and so does your professor. So there's no need to write the word radians. What about beta? Beta is negative pi. Well, again, standard position, so I have an array emanating out along the positive x-axis, but it's a negative angle. So I'm going to rotate backwards. Now, here's the deal. If all the way around was 2 pi, halfway around is half of 2 pi or pi. So halfway backwards, which is negative pi, will be where we land there. That's our terminal side. That's, you know that as 180 degrees. I'm just calling it negative pi. That's what beta is. And so once I said, you know that as 180 degrees, there is a way to transform between radians and degrees. You can kind of see it. If pi is 180 degrees, or in this case, negative pi is negative 180 degrees, and 2 pi is 360 degrees, well, that is our conversion. So, but we'll get to that in a different video. What about this angle pi over 4? Here's terminal, or the initial side, sorry. Pi over 4, let's see. Well, it's a positive angle, so I know I'm going to open up. Let's see, if I know that all the way around is 2 pi, and halfway around is pi, so we wouldn't have made it, for example, we wouldn't have made it all the way over here. That's pi. Well, what about half of pi? Well, half of pi is pi over 2, so that's still too large. The denominator on pi over 4 is larger than 2, so that pi over 4 is smaller than, it's actually half, technically. Pi over 4 is half. Pi over 4 is equal to 1/2 of that pi over 2. So we just are halfway up to that pi over 2. So halfway up to that pi over 2 would look something like this, which is probably what you could consider to be 45 degrees. That is, what is that? Theta is equal to pi over 4. That is an angle you must get used to drawing. Pi over 4 is very popular in calculus and trig. The last one's there just to make sure you're awake. Phi is, or phi, is pi degrees. We drew that earlier, and notice it has the degree sign. That means we're working in degrees, not radians. So phi or phi will look like what we drew earlier, which is a very shallow angle. And we'll just draw this in here like that. Phi is equal to pi degrees. Again, because it's in degrees, so it's 3.14 degrees. I'll actually state that right here. Approximately 3.14 degrees. And finally, let's go ahead and do what we did last time with the degree examples. Let's name 6 quadrantal angles, but in radians this time. So quadrantal angles, as you should recall, are angles that terminate on an axis. So we know, for example, all the way around would be 2 pi. So theta 1 equals 2 pi, totally doable. If we didn't go all the way around, but instead only went halfway around, that lands on an axis as well. So half of 2 pi is pi. If we didn't go all the way to pi, but only went halfway to pi, that lands on the y-axis. So half of pi is pi over 2. Let's see, now we have to start doing other things, right? We can get really creative, but let's go ahead and do some negative angles here. Let's suppose that you want to rotate backwards to here. Let's pretend that's where you want to land. Well, notice you went all the way to pi, negative, right? Negative pi, and then went another half of that. So you went to negative pi and then lost another half of it. That's negative 3 pi over 2. Let's see, let's do another one. It's basically all you're doing is either adding pi's or pi over 2's, or you could add 2 pi's. Let's suppose that I start, again, standard position, so start on the positive x-axis, rotate around, let's rotate around 3 times, plus a half. So rotating around 3 full times plus a half. Well, that's 3 sets of full rotation. So 3 sets of 2 pi plus another half, plus a pi over 2, because we went up a quarter, basically, half of pi. So up a quarter of a full rotation. That's 6 pi plus pi over 2, or 13. Yeah, 13 pi over 2. And we have 1 left, so might as well just do something negative here. Let's suppose that we want to land down here, right here, eventually. Let's rotate. Let's just make it simple. Let's rotate like that. Okay. You went backwards a full 2 pi. So I went backwards a full 2 pi. That gets us all the way over to here. And then half a pi beyond that. So another half a pi beyond that. There you go. So what is that? Negative 5 pi over 2? You just have to be used to quick fractional arithmetic. That's all. But yeah, so there's radian angles for you. You'll be playing with them for the rest of this course, and pre-calculus and calculus and all that fun stuff.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.